Hello friends, welcome to my YouTube channel RF Design Basics. So in this video we will be seeing the Laplace transform pairs. That means what is the Laplace transform of given function into the frequency domain and what is their inverse Laplace transform. So first function is delta t, which is called impulse function. For impulse function Laplace transform will be 1. So if you have any constant, you can convert them into impulse function. Then second function is u of t, which I have also done in the last video. U of t is unit step function and the Laplace transform is 1 by s. So if you get anything like 1 by s, you can convert them into unit step function. Similarly, e to the power minus at, the Laplace transform is 1 by s plus a. So if you have something like 1 plus 1 by s plus 2, we can convert them into e to the power minus 2t. Similarly, if we have a function t ut, so in this all function ut will be by default multiplied. So for t function, we have 1 by s square. So just in 1 by s, another s is multiplied. Then t to the power n, we have this transformation. So likewise, this table can be referred whenever we need as per the requirement of inverse Laplace transform. Something is in this form, we have to write the inverse Laplace transform of that as t into e to the power minus at. Then there comes few properties of the Laplace transform. So these are linearity, scaling, time shift, frequency shift, time differentiation, and so on. Linearity is if you have a function f1t, f2t, and both are multiplied with some constant a1 and a2, its Laplace transform in frequency domain also will have this similar property. So it will have f1s multiplied with a1, f2s multiplied with a2. Scaling, it is f80. So the scaling means here we have f80. So it can be 1 by a, f, s by a. So if you multiply time with a constant, that constant will be like 1 by that constant, and then f of s by the given constant a. So this is called scaling. Similarly, there is time shift. So time shift means you have subtracted a in the time. So t minus a, here also t minus a. So there will be a function e to the power minus as which will be multiplied in this. You can see here. So likewise, you can refer all these properties of Laplace transform, which will be very useful when we do inverse Laplace transform for any function or even the Laplace transform of any function. So now I will take few examples of the inverse Laplace transform. As we already know this sinusoidal and cos omega t, what will be their transform. So if we get any function like this, we can convert them in this format. I can also explain this sin omega t and cos omega t for the Laplace transform, and then we will go ahead with the inverse Laplace transform. So let's take sin omega t first. So our function is ft sin omega t u of t. So we can find out the Laplace transform as 0 to infinity sin omega t e to the power minus st dt. As these are two different functions, and also we know the conversion of sin omega t in the form of e to the power theta, Euler's form. So sin omega t can be written as e to the power j omega t minus e to the power minus j omega t divided by 2j, that is sin omega t into e to the power minus st dt. Now next is here e to the power j omega t e to the power minus st. we can combine them. It will become e to the power minus of s minus j omega t dt, 1 by 2j in common. First integration is this, then second integration will be minus 0 to infinity e to the power minus j omega minus s, so minus of s plus j omega t dt. As we know that if we have any function here, then what will be there? Laplace transform, it will be 1 by s minus j omega. Similarly for this it will be 1 by s plus j omega, so minus 1 by s plus j omega, which can be further calculated as 1 by 2j s plus j omega minus s plus j omega divided by s square plus omega square, which is equal to, s is cancelled, j will also be cancelled, and 2 will be also cancelled, so we have omega by s square plus omega square. So if your function is ft is sine omega t, its Laplace transform fs will be equal to omega by s square plus omega square, so which we can verify over here. You can see it's omega by s square plus omega square for sine omega t. Similarly for cos omega t also we can do. So what we have to do is just take the function as cos omega t, so we can write fs as 0 to infinity cos omega t e to the power minus st dt. This can be converted into e to the power j omega t plus e to the power minus j omega t divided by 2 from the Euler's formula into e to the power minus st dt. This is 0 to infinity. It's 1 by 2 common. Here we have minus s plus j omega, that means s minus j omega, so 1 by s minus j omega plus similarly 1 by s plus j omega. So the difference between sine and cos is there is a plus sign over here and there is no j over here, so it is s plus j omega plus s minus j omega divided by 2 into s square plus omega square. So this j omega cancelled. We have s divided by s square plus omega square, which is the Laplace transform of cos omega t. That means if you have cos omega t, then omega square will be here, s square and s will be here. So this way we can find out the Laplace transform of different function, and whenever required we can refer this table for getting the pair of Laplace transform. So in next video I will be doing inverse Laplace transform of few functions. Thank you.